So we'll look at the Gaussian integral and some other related integrals that arise frequently in physics. So the Gaussian integral is integral from minus infinity to infinity e to the minus x squared dx. So to evaluate this integral, we need to square it first. So if I call this I, then I squared will be, so this is the square of this integral. And here I've used two different variables x and y, but since they are dummy variables, so it doesn't matter. And now we see that this product of these two integrals can be written as a double integral like this. And this, of course, here is the product of e to the minus x squared and e to the minus y squared. And you can easily see this by first starting with this double integral and then showing that this can be reduced to the product of the two integrals above. So now we have this integral. This can be easily evaluated in terms of polar coordinates. So in polar coordinates, x squared plus y squared will be r squared, and this dx dy will be r dr d theta. And since we are integrating over the entire xy plane, so to cover the entire xy plane in polar coordinates, we need to let r grow from 0 to infinity and theta from 0 to 2 pi. So we have this e to the minus r squared, and this is r dr d theta. And now we see that we have an additional factor of r here, and this makes it easy to evaluate because we see that the derivative of e to the minus r squared is minus 2r e to the minus r squared. So we have a factor of r there. So this can be written as, and this integral will be minus 1 over 2 e to the minus r squared. And at infinity, this is going to be 0. And at 0, this is going to be minus 1 over 2. So this is, and now if we evaluate this integral, this is going to be pi. And so the square of this integral is pi. Therefore, the value of this integral is square root of pi. So we have this result here. So we now move on to some similar integrals. So let's see this integral. So here we have a factor of alpha here, and for this is a very simple substitution we can use here. U equals square root of alpha x, then du will be square root of alpha dx, and this is going to be integral from minus infinity to infinity e to the minus u squared du, and we have a factor of over square root of alpha. And using this above result here, this is going to be square root of pi over alpha. So this integral e to the minus alpha x squared dx, this is square root of pi over alpha. So we now move on to some other integrals here. So let's consider this case where we have this x to the n being multiplied by e to the minus alpha x squared. So here n is an integer, and we have two cases here. N can be even or it can be odd. So first let's check if when n is even. So in the case when n is even, we have integrals like equal from minus infinity to infinity, x squared e to the minus alpha x squared dx. So integrals like this can be easily evaluated using integration by parts. But there is one another technique that is simpler than this, and we can quickly do it using the technique. And the trick is to start with this integral e to the minus alpha x squared dx, and we know that this is square root of pi over alpha. And now what we'll do is differentiate both sides with respect to alpha. So we see that this is just a function of alpha here. So we can differentiate both the sides with respect to alpha. So this is going to be partial derivative with respect to alpha e to the minus alpha x squared dx, and this derivative is going to be minus 1 over 2 square root of pi over alpha to the 3 over 2, and this is just square root of pi over alpha cube, and this derivative here is minus x squared e to the minus alpha x squared, and this is, so we can cancel the minus signs here, and we'll end up with x squared e to the minus alpha x squared dx. This is 1 over 2 square root of pi over alpha cube, and so we have this result for x squared here. In order to get the value of this integral for the higher exponent of x, like x to the 4 and so on, we can differentiate again with respect to alpha. So if we differentiate both sides again with respect to alpha, we are going to get the result for x to the 4, and it turns out to be this integral x to the 4 e to the minus alpha x squared dx. This integral is 3 over 4 square root of pi over alpha to the 5. And to get the higher powers, we can continue differentiating both sides with respect to alpha, and we'll get the value of this integral for higher even powers of x. So now we move on to the case where this n is odd. So in case of odd n, we see that x to the n is an odd function, and e to the minus alpha x squared is an even function. And since the product of an odd and even function is an odd function, so this integral is going to be 0 for odd n. So this is 0 for odd n. So we can consider this integral from 0 to infinity x to the n e to the minus alpha x squared dx for odd n. So for case n equals 1, we have this integral x e to the minus alpha x squared dx, and this is very easily evaluated. We notice that the derivative of e to the minus alpha x squared is minus 2 alpha x e to the minus alpha x squared. So this is going to be minus 1 over 2 alpha to the minus alpha x squared, and evaluated between the limits 0 and infinity. So at infinity, this is going to be 0, and at 0 is going to be minus 1 over 2 alpha. So this is 1 over 2 alpha. So for this case, So we have this result for the case n equals 1. For the higher powers of n, we use the same technique that we used before, that is differentiating both sides with respect to alpha. So if we do that, we saw that differentiating both sides with respect to alpha brought out the factor of x squared here. So if we multiply this x by the factor of x squared, we will end up with x cubed. And if we again differentiate it, then again we are going to break down the factor of x squared, and we will end up with x to the 5 here. And so like this, by differentiating both sides with respect to alpha, we can get the value of this integral for odd powers of x. So if we differentiate both sides with respect to alpha, we get, so the derivative of this with respect to alpha is going to be minus x cubed e to the minus alpha x squared, and this derivative with respect to alpha is going to be minus 1 over 2 alpha squared. And if we cancel the minus signs here, we end up with x cubed e to the minus alpha x squared dx equals 1 over 2 alpha squared. So this is the result for x cubed, and differentiating both sides again with respect to alpha will give us the result for n equals 5, and that turns out to be x to the 5 e to the minus alpha x squared dx. This is 1 over alpha cube. So now we have covered both the cases for odd and even n. So that's it. Thank you for watching.